Yeah, so we'll just get started. So real quick, we're going to give a quick introduction on what exactly WarpStream is for those that might not be acquainted. All right, so what is WarpStream? WarpStream is really similar to Kafka. It's got topics, consumer groups, partitions, pretty much everything that Kafka has. So if your application uses Kafka, chances are it can probably also use WarpStream. So what are the differences? Some of the major differences are compared to traditional Kafka's brokers, WarpStream now has a concept called agents. So what are agents? Agents are really similar to brokers in that they are the interface for Kafka clients to talk to the cluster. But they're a little bit different. So the way that WarpStream kind of innovates here is by separating the data plane and the control plane. So if we take like a traditional Kafka broker, right, we have your storage volumes on the broker. Instead, WarpStream opts to separate that out, and it uses blob storage, such as S3. So this kind of gives this zero disk architecture, which provides some benefits. So one thing is that it can potentially lower the storage costs of running WarpStream agents. So for example, the cost difference between an EVS volume versus using S3. In addition, it can also help to lower inter-AZ networking costs. It does this because S3 takes care of the replication so that the Kafka brokers do not have to replicate across those AZs between themselves. Also, with this new zero-disk architecture, these agents are now stateless compared to Kafka brokers, and that also lets scaling take place much easier. And finally, we have the data that never really leaves your cloud because it's provisioned in your own S3. All right, and I mentioned that it kind of also separates the control plane out as compared to a traditional Kafka broker that uses KRaft or Zookeeper. And this control plane is managed by the WarpStream cloud, so that controls all the metadata for the cluster, and that is managed by Confluent. All right, so this is a little graphic that we stole from WarpStream's website, just to kind of illustrate the flow of data here. So you can have your, your Kafka clients, your producers, consumers, and then they only interact with the WarpStream agents in red. And then the WarpStream agents themselves, they read and write data to S3, and then they only read and write metadata to the WarpStream cloud. And so, yeah, as I mentioned before, these agents are stateless. So you can see there's like zero ops auto scaling. And one other thing that's really interesting is that you can actually configure the WarpStream agents to kind of talk to clients or prefer clients in a certain availability zone. And that also helps to further reduce the cost of inter-AZ networking fees.
One of the interesting things about the amount of workload that our clusters get is that it's very cyclical. It is directly tied to when the US stock market is open. So during the hours that the stock market is open, it's when we have the highest amount of traffic. Outside of those hours, we usually experience way lower amount of workload on our clusters. So if we have something that is elastic, it would allow us to save a big amount of money by scaling down when we don't have that much traffic come through our website. Which gets us into the reasons why we decided to do this migration in the first place. So cost is one of the biggest reasons. Because we have an elastic, because WarpStream has the ability to be elastic compared to Kafka, we're able to scale down. There are also other features that come along with this. Ethan already mentioned that we want to bring down inter-AZ costs, and WarpStream is primed to be able to let us do this because we ended up using S3 as our storage layer. because we use S3 as our storage layer, we don't really have to worry too much about how the data is replicated. S3 takes care of that for us. Again, in terms of cost, S3 can be cheaper than EBS. And finally, we don't really have to worry about running out of storage, since S3 is pretty much infinitely scalable. Now, you might notice that we put that the control plane is managed as both a pro and a con. One of the things that is a pro about having the control plane be managed is that we don't have to deal with its complexity. So that is out of sight, out of mind, while it is working well. But if we run into any issues, then we have to triage ourselves, and that's when the cons come in, because we have to figure out if it's something that we did on our side, or if it's something that happened in the control plane itself, which then would require us to file a ticket, and it introduces a little bit of friction in how we deal with any issues that our clients might be encountering, or that our WarpStream clusters might be encountering. Then there is also the fact that we have to pick workloads that are suitable for WarpStream. So one of the cons of moving to WarpStream is obviously that we take a hit in latency. So we have to pick workloads that are adaptable to that. Okay, so we've talked about our reasons why we wanted to migrate to WarpStream. Let's talk a little bit about how we ended up laying out the components of WarpStream in our infrastructure. So at the base, we have the agents, which we decided to model as a pod. We decided to go with a one pod to one node approach. This was upon the recommendation from WarpStream. It just makes things easier to handle. You don't have to deal with noisy neighbors that can cause you issues if anything else gets scheduled on that node. These agents, as Ethan mentioned, are responsible for interacting with the clients. Next, we have the agent groups. And agent groups are a collection of agents that are basically under a namespace. And we modeled this as a deployment in Kubernetes. One thing I want to point out, which will become important later, is that an agent group can be composed of multiple different Kubernetes deployments. And with having an agent group, we can assign particular clients to agent groups. And the reasons why you would want to do this is because you might want to have different configurations for different agent groups. For example, we might want to have TLS enabled for one agent group, while we want to just have plain text for another. Or if you have a particularly noisy client, maybe you want to use an agent group to isolate that client from other groups or other clients that might be talking to that agent group. Or you might actually have a client that's so important that you have to guarantee resources for it. So by assigning it a particular agent group, you are protecting it and allowing it to have the resources that it needs.
All right. So yeah, as Renan mentioned, there are a few kind of constraints or things that you should be aware of when using WarpStream. And so one of them is the latency. And so when we were selecting our use case, logging is a perfect candidate. Latency is not super sensitive. And given our traffic patterns, it's also something that's pretty elastic. All right, so to just give a quick overview, I'm going to walk through kind of our migration. And we're going to start here at our status quo, or how our kind of landscape looked before WarpStream. And as a quick background, we do use Vector, which is a tool for building observability pipelines. If you're not familiar, you can just think of it as a Kafka client that can act as a producer or consumer. So to take the life cycle of a log, basically, this is the logging setup for our Kubernetes clusters. So we have a daemon set that has a vector pod, a vector producer that runs on every single node in the cluster, shipping logs to Kafka. And then once it's buffered in Kafka, we then consume it with our vector consumers. Then those vector consumers ship off those logs to our logging service. And our logging service itself uses Kafka as well as its backend to process and persist these logs. Our key insight here was trying to break down the cluster or break down this migration into two parts. So we kind of separated it out into part one, which is the logging service itself, and then part two, which is the rest of the log shipping. And as part of this migration, we also wanted to break apart this monolithic Kafka cluster and use two WarpStream clusters in the end, which I'll show later. All right, so the first part was the logging application migration. So just some background on our service that we use. Its Kafka setup is kind of all or nothing, meaning that we can't really move bit by bit over to WarpStream. It kind of has to happen all at once. So our goal here really was to make that swap happen with as little impact as possible. Now, when we say as little impact as possible, what do we mean by that? We kind of mean we want to have as little disruption to the log viewing experience for our engineers, as well as no dropped logs and no duplicated logs. All right, so how do we do that? Our strategy here was first to cut off the log ingestion to our logging service from Vector. And then step two, we wait until our logging service has finished processing and persisting all these logs. And then once that's kind of happened, this downtime that we incurred was just a couple minutes. We did this over a weekend. And the switchover happened to WarpStream at that time. And then finally, our third step was to finish the switchover and then re-enable log ingestion to the service. So at this point in the migration, our logs were still shipping to Kafka, and then our Vector consumers were shipping logs to our service, and then our service was fully on WarpStream. All right, now here's part two, which is the Vector log shipping section. Again, we wanted to keep similar goals, so no duplicate logs, no impact on the log viewing experience, minimize disruption. But we also wanted to have as much gradual rollout and rollback as we could, which we couldn't have in part one due to the nature of the application. So our key insight here this time was to create two different sets of Vector consumers. So we had the original set of Vector consumers consuming from Kafka and shipping the logs to our logging service, but then we also created another copy set that was consuming from WarpStream. So what this allowed us to do is basically, no matter what cluster our Vector producers were producing logs to, it would always make it to our logging service, which was really important for us so that we didn't drop any logs. And it's really nice as well that there's no duplicates because any producer can only be producing in this setup to one of the two clusters. So yeah, we did a gradual rollout, as you can kind of see from the before picture. 100% of the logs were going to Kafka, and slowly we kind of dialed that number up to 100% on WarpStream. And that worked out really well for us. All right, and yeah, so this is kind of how our logging setup looks now. The logs get shipped to the WarpStream logging cluster, then consumed by Vector, shipped off to the logging service, and then the logging service is using its own WarpStream cluster for itself. Now that we kind of walked through the migration that we conducted, we also wanted to talk about kind of how we set up the control plane. So as mentioned before, the control plane is the WarpStream cloud that manages all the metadata for each WarpStream cluster. And in that, it has its own version. So when it comes time to upgrade these versions, it kind of posed a problem to us, and that's because the control plane is a regional multi-tenant service. So when these upgrades happen, they happen all at once for a region. And it's also for multi-tenants. So this timing of the update or the upgrade isn't really within our control. So enter the WarpStream single tenant control plane that we purchased from Confluent. in this world, we are the only tenant in the service. And so that gives us more control over when these upgrades kind of happen. And what that allows us to do is to do some lagging upgrades. So for example, I'm going to walk through an example real quick here. All right, so this is kind of the base state of the world, right? Let's say we had the single tenant control plane and this shared tenant control plane. And we have a few pre-production and production clusters on each of these, WarpStream clusters, that is. Now let's say Confluent comes out with a new version of the control plane. Well, that update is going to happen on the shared tenant control plane first. And this is going to give us some bake time to make sure that no issues arise in pre-production. And we can catch any issues before they hit our production clusters, so we can really protect what's important. Now, after that bake time of however long, we have an agreement with Confluent for about a week or two. The version upgrade will then be rolled out to the single tenant control plane, and now all the clusters are on the newest versions. Now you might ask, why do we have a production cluster and a pre-production cluster on that single tenant control plane? Well, that's because we wanted to make sure that at any point in time during these upgrades, in case there was any production issues, we always had at least one pre-production WarpStream cluster that we could use to test that had the exact same control plane version as well as agent version to debug.
Okay, so one of the other things that WarpStream allowed us to do was tackle this use case that a lot of teams came to us with. So as Robinhood has grown in its size, one of the things that we've wanted to do is to run workloads in separate accounts. In the past, in order to do this, we needed to find a way to have a path from one VPC to a different VPC where we were running our logging infrastructure in order to ingest that data. As you can imagine, that involved setting up PrivateLink and doing a whole bunch of other things in order to allow that to happen. With WarpStream, we have a different option. Instead of doing that, we just allow permissions to read and write from the S3 bucket that WarpStream has. And so from there, we just run agent groups in both different VPCs. And then, as you can see in the diagram, the application talks to one agent group in order to ship the logs. Those logs get written to our S3 bucket for our WarpStream cluster. And then in the other VPC, we have other agent groups from which the logging service consumes those logs. So that makes it a lot easier to set this up. It's a lot less chaos for the team to maintain it. And it is a great feature that we have been leveraging with WarpStream. All right, so that concludes how we did the migration. Great success, right? We finished doing this. Our leadership threw us a party because of all the money that we saved. But the real story is that we had to do a bunch of work to really eke the savings out of WarpStream. For one thing, we had to fine-tune the components that were part of our WarpStream cluster. So we already talked about having one pod per node, which means that we eliminated the noisy neighbor problem. The next was we needed to choose an instance type. Since we run on AWS, the choice was pretty simple. WarpStream has a whole bunch of instances that they recommend. And typically, the recommendation is that you have one core for 4 gigs of memory and a whole bunch of bandwidth, since we're going to be pushing a lot of data through these agents. The next challenge, and these two are kind of interrelated, is whether we wanted to have bigger instances or smaller instances. If you have bigger instances, you're able to keep the number of agents relatively small, but that means that when you're running at low capacity, you're still running with maybe more capacity than you actually need. In contrast, if you have smaller instances, you might be able to right-size your the amount of compute that you're using to match the load that you're getting better. However, running more agents actually has some hidden costs to it. For example, since S3 is API-based billing, if you have more agents, you're actually incurring more API calls. So we took all of that into consideration, and we decided to settle upon running about 6 instances when we were running at very low capacity on our clusters. We'll talk about why 6 in a little bit. But the other thing that we also had to get right was the HPA, the horizontal pod autoscaler policy, because that is really what makes our elastic service or leveraging WarpStream as an elastic service work. So we took the recommendation from WarpStream. We are scaling based upon CPU. And the next recommendation from WarpStream was we wanted to have fast scale-ups. So whenever we hit a spike in traffic, and we experience these fairly often because, as you can imagine, the amount of workload for Robinhood is really influenced by events happening around the world. So at any given moment, an event might go out, and we might get hit with a lot of logging because all of our services need to scale up. So we wanted fast scale-ups, but we also wanted to be very careful about scaling down. So this is the key part of saving money because we don't need that capacity, so we're able to shut those instances off. But in the beginning, we were shutting them off very quickly without having configured them to do graceful shutdowns, which resulted in huge latency spikes for our logging service. What we ended up having to do was to configure the agents so that they would have an extra amount of time so that they would basically move the connections from one agent to another that wasn't going away, and that really reduced the amount of latency that our applications were experiencing. So let's add another dimension to autoscaling. Now, we mentioned that one of the goals for us was to reduce the inter-AZ network traffic. This is a big item on our AWS bill, so we wanted to bring that down, and we wanted to leverage WarpStream to do this. WarpStream allows us to do this by adding a hint to the client ID, which tells us, or tells WarpStream, where the client is located. The WarpStream control plane does some magic, and then it reassigns that client to an agent which is running in the same AZ as that client. As you can imagine, we do not have a homogeneous amount of workload spread evenly across all AZs. So this introduces another challenge, which is how do we scale for each one of those AZs independently? The approach that we took was to create 3 different deployments, each one of them tied to a different zone, and we attached an HPA to those. Now, I mentioned earlier that we settled down on running 6 instances. This is the reason why, because we wanted to have 2 instances per AZ running at all times.
All right. Next, we're going to talk a bit about latency trade-offs. So as we kind of mentioned before, hopping onto WarpStream, you're kind of trading off some latency, some added latency from using S3. Luckily, WarpStream provides some levers that you can use to kind of adjust this trade-off for how much latency you can tolerate. So for us, if we look at this graph, it starts at around 0.25 seconds. And so that increase there is where we doubled the batch size. So the batch size, this is the batch size of data that's coming from the agent to S3. And so the larger batch size that we use results in less S3 requests, as Renan said earlier. And the less S3 requests we make, we save more on our S3 bill. The trade-off here is with larger batch sizes, you're going to be waiting around a bit longer for those batches to fill up. And so that increases some of the latency in the cluster there. Now, the good news is there's also another option. So if low latency is required, WarpStream also provides compatibility with S3 Express, which can help lower that latency for you guys. But disclaimer, we haven't really played around with it too much or used it ourselves, but it is there.
Okay, so we've concluded our migration. We tackled all the challenges that came up. So what did our actual outcomes look like? We can't give exact figures, but we're going to be talking about this in terms of the 7-day moving average peaks. So compared to when we started running WarpStream, when we first did our migration, compared with the last month, we brought down the inter-AZ network cost by 99%, the compute costs by 47%, and our storage by 34%. And more importantly, how does this compare to what we had before? So the 7-day moving average for Kafka is going to be pretty much the same because it's a static service. We don't try to scale it up or down. But in comparison with the amount that we spent on WarpStream with a comparable cluster, we were obviously able to bring down the inter-AZ costs by a huge amount. We basically got rid of them. We were able to save on compute, and we were able to save a little bit on storage. We still believe that there are a few more tweaks that we can do to extend those cost savings on the storage side, but for now, these are the savings that we've achieved. And a big part of this is having WarpStream be elastic so that we can scale down during the off-peak hours so that we are not using those components and therefore saving on our bill. Now, I want to point out that these cost savings are not apples to apples because we still have some other workloads running on the other Kafka clusters, but it gives a good kind of ballpark estimate on how much you would be able to save on a pretty high traffic cluster. The other thing that I do want to mention is that this does not include the cost for running WarpStream itself. So those are added costs, and those are a per usage cost. And in order to get those, you should talk to your favorite Confluent representative to get those numbers. One of the big things for us was achieving operational efficiency, and WarpStream really has allowed us to do that. We don't really spend any more time dealing with the EBS volumes, increasing them, or making changes to our Kafka cluster that are very labor intensive. We don't have to really deal with URPs anymore when it comes to these clusters because, like I mentioned before, S3 takes care of replication for us. It brings that data up in all of our AZs. And the automation that we've created to manage our WarpStream clusters has made it so that we are able to spin up new WarpStream clusters in a matter of hours. All of this has resulted in saving our team a whole bunch of time from on-call burden and operational duties, which allows us to really focus on other important problems that our company needs to solve. We wanted to give a shout out to all the folks that helped us get here, the rest of our team. The observability team from Robinhood was a big help in this. Our infra leads who helped us manage the complexity of doing this migration. And obviously, we want to give a huge shout out to the WarpStream team who have been there since day one for us and have been super helpful in helping us resolve any issues that we ran into.
Yeah, I guess that concludes our talk then. Thank you so much for coming.